Okay, so today I'm going to continue with the network layer, and I'm going to talk about basically what happens when you set up something in a small network, in a local area network, or LAN as we call it. So this is pretty much what you would do if you were setting up something at home or in a small lab or a small company. And some of you have probably done this already. I don't know, probably if you have a laptop or a desktop, anything like that, you probably had to do these things. And hopefully at the end of the lecture today, you have a better sense of what you were doing and why you're doing it and how it all fits together. Okay, I'm going to start with something you probably know about and you've seen before, which is this issue of public and private IP addresses. So the IPv4 address space is 32 bits. And we already know that it can be broken up using this slash notation to chunks, /8 or /16 or /20 or whatever, which are aggregate chunks. The problem with IPv4 is 32 bits is that 2 to the power 32 is approximately 4 billion. And we have, at this point, more than 4 billion devices or endpoints on the internet, something like approximately 7 to 8 billion, and doubling in the next few years. So how do we do that? I mean, and the answer is that we reuse the same address more than once. And the way we do it is that we have these, what we can think of as private address spaces. And the private address spaces reuse the same address over and over again. And they all have a single public address. And so what we have to do then is that we have to make sure that these private addresses don't leak out of these private address spaces. To be more precise, in the internet, there are actually three ranges of private address spaces, three ranges of addresses which are private. They cannot be used in the internet core. Okay, they have to be private, and these ranges are essentially 10 dot star, which was /8, and 192.168, and this 0.0/16, and this is /24, which I can never remember, 172 dot something something. I don't know what it is, but most of the addresses are basically over here. And this one is probably, if you ever set up a Wi-Fi access point or a home gateway, almost always they use a 192.168. And most of you, when you did your assignment 1, and they asked you to do ifconfig or ipconfig to find out what your IP address is, you were reporting a 192.168 address because it's a private address that is actually part of your local private address space, especially if you did it from home. That's what you would see. So most of you have seen this 192.168, right? So let's take an example just to see how this works. We have 192.168, let's say .0.1, and there's a 192.168.0.1 address here as well. So the same address is repeated twice. That's okay from the source perspective, but imagine they're both connecting to the same server over here. Okay, and this server is some server. When it sends a packet back, to begin with, it can't use a 192.168 address because that address is prohibited in this space. And second, how do you know whether to go here or to go there? Okay, and so that's where this network address translation, or NAT, comes in. So these two topics are basically very closely related. So public and private addresses are kind of go hand in hand with network address translation, because without that, you really can't communicate to the public internet. Now, you could, of course, have a local area network that is completely isolated from the rest of the world, right? You could just have a network in this room, for example, where all the addresses were 192.168, and then you wouldn't have to worry about NAT. But if you want to talk to the outside world, then you do need to have some kind of translation in the middle, and we'll see in a minute how that's done. Okay. I should add that if you have a private space where you're not talking to anybody else, you can use any address you want. It doesn't really have to even be a private address space. After all, you're not going into the core internet anyway, so it doesn't really matter. Okay. So the private addresses allow you to essentially make the address space much, much larger than it actually is because of this. And this is one reason why IPv4 is still surviving even after all these years, because the sense that we were running out of IPv4 addresses was already like a crisis point in 1992. 1992, I remember a big series of discussions on what's going to happen, and we're going to run out, and so on and so forth. And then around 1994 or 95, a guy called Paul Francis, who's actually a researcher, he's in Germany right now, he and some of his co-workers, co-authors came up with this idea of network address translation, which I'm going to show you in a minute, and suddenly the whole problem was solved. Then it just went away, and so we still are continuing with this, and that's why IPv6 is always 1 year in the future, because we've got to pretty much have this problem solved for the near term. So let's see how this works. Okay, any questions about this so far? Private addresses and so on. So private address is basically an address that you're allowed to use in your own private network as you wish. There's no need to go to Aaron, no need to go to a registrar, Rogers, whatever. Just use it as you wish, right? It's like saying I have a phone, a cell phone, and I can put in a particular number on it, right? I can put 519-888 something, and as long as it's 519-888, I can do whatever I want with it. I can have my own private phone, right? Like a walkie-talkie system. That's what this corresponds to. By the way, the 10.8 has a very interesting story. Just a brief historical note. The first network on the internet stands for inter-network, okay? And in a minute, I'll tell you why we call it inter-network or how IP fits into it. But inter-network really means I have two networks and I'm connecting them together, okay? We can think of connecting two subnets together with this core. That would be an inter-network, okay? And the 10.* address was first used for the first network on the internet, which is the ARPANET. So ARPA stands for Advanced Research Projects Agency. It was a Department of Defense funded initiative. So in 1967, I believe, the Department of Defense said we want to fund computer networking because we think the military can use it, and they gave a bunch of money to Stanford, to UCLA, UC Santa Barbara, and Stanford Research International, SRI, and said, okay, go build this network. And they did, with help from a company called BBN, Bold, Beranek, and Newman. And they had 4 nodes on it at these specific places: Stanford, UCLA, Los Angeles, Santa Barbara, and Menlo Park, which is where SRI was. And that was called the ARPANET. And the addresses there started with 10.*. In I think it was 1989 or 1990, they turned off ARPANET after about 20 years. And when they turned it off, they said, okay, we're going to, just like when they retire a basketball player, they put the number, retire the number. Is that in basketball or baseball? One of these ball games. I don't know which one it is. So I can't distinguish between the two. They both have a ball in the title. So, and they both waste lots of time. This one is the ARPANET number. It's been retired, right? So 10.* is, the famous net 10. Net 10 is, of course, a palindrome, which is even nicer. So net 10 is the ARPANET. And so we remember it fondly with the 10.* address space. Okay, enough of nostalgia. Let's look at NAT for a moment. So the way that NAT works is like this. It says, okay, we don't have enough IP addresses, but guess what? We have more than enough TCP port numbers. Okay, we have more than enough because, each end host has got 16-bit ports, 65,000 possible sockets, but we're never going to use more than a few, right? We don't need that many. So why don't we reuse the TCP port number space? And the way it works is like this. Let's kind of explode out the subnet over here, the private subnet. And we have the NAT gateway over here. But by the way, did Andy cover NAT at all, or no? Okay, good. So, and here we have public server. So here's your public server, and let's give it an address, a nice address, 128.32.16.8. Now that's a very nice number. It's all powers of, well, it's not exactly powers of 2, but it is, it is powers of 2. 128.32, as you can imagine, is a very highly sought-after prefix, and that's Berkeley. So they were there earlier. So they got early in the internet, so they got 128.32. And so that's a server somewhere in Berkeley. And so here's your NAT. Here's your home gate. It's 192.168.0.2, for example. And that's your laptop. That's it, at home. Now, what you want to do is to arrange for the private address to be talking to this public address, okay, and for it to talk back, okay, have a bidirectional system. Okay, that's the goal, and we'll see how it's done in just a moment. Everybody clear with that? Okay. Remember that this 192.168.02 cannot actually go on this link from here to there. If it did, it would be dropped, okay, because in between is, of course, your internet cloud, and that internet cloud, the minute it sees a private address, is going to drop it. So we're going to have to change it somehow, okay? So the way we do it is that this NAT gateway is given a public address, and let's say it's given a public address of 129.97.75.1. Let's say that's the public address of this NAT gateway. So what we're going to do is that whenever we take a packet going from this laptop into there, the source address is going to be changed. The source address, instead of being 192.168.02, is going to be replaced with 129.97.751. Okay, we're going to change it, and that's a perfectly reasonable thing to do, right? Because that's a valid source address for it to go to, and so it's going to go like this. So in the packet header, the source address field is going to be rewritten with this new address over here, 129.97.751, and off it goes to this destination over here. This destination sees the source address of 129.97.751 and says, sure, no problem. It's a public address, and it replies back to the gateway with its source address set to 128.32.16.8, and the destination set to 129.97.751, and it goes to the NAT gateway. At this point, the NAT gateway says, okay, I have a response from here, and it has to maintain some table. It's called the NAT table, which says, if I get a response from that source, then I have to rewrite the address and send it back over here. I'm going to rewrite the source address and destination address and send it back over here. So we're going to have to keep this little switching table, which looks very much like a virtual circuit switching table. Okay? What the virtual circuit switching table says is, if I get some address that comes in here, the destination doesn't like it, I'm going to change it and send it over there, and off it goes. Very much in the same way, we're going to do that kind of table. So let me write the table down over here. So it says, if the source address, okay, is 192, this is the NAT. If the source address is 192.168.0.1, okay, let's ignore this for now. I'm going to set and the destination address is 128.32.16.8. Okay, if that's it. All right. So if the packet is coming from this source and it's to this destination, I'm going to rewrite it. Okay, I'm going to rewrite it with me being the source. Okay, and if the source is 128.32.16.8, I'm going to rewrite the destination as 192.168.0.1. Okay, so if you did this, it's almost going to work, but not quite. Okay, and the reason it's not going to work. Okay, so can somebody tell me why it's not going to work? This over here. What problem would, if you just had this in the NAT table, what problem would you have? Yeah, some other source, let's say another laptop over here, or it's your V box, okay, and this one is connected over here and also talks to the same destination. What happens is, okay, so here we have 192.168.0.3, for example. That's okay. When it goes over here, it's going to rewrite it. It goes to that destination. But when it comes back over here, this NAT box doesn't know what to do. It says either it's going to go here, it's going to go there, but I don't know which one it is. Right? Do you see the problem here? Yeah. Oops, sorry. Yeah. 2. Yeah. So what I'm saying, I think what Ryan pointed out is that if you had a .3, outbound is okay, but inbound we're in trouble, because when you come over here, this table is not enough for us to tell us which way it goes. Is that clear? So we have to put some additional something. And what the additional something is that in addition to changing the source address, we also change the TCP port number. Okay? And so what we do is that on this outbound link over here, this only works for TCP, by the way. It's not, you have to do something special for UDP, separate for TCP. But for TCP for now, what we do over here is that the NAT device is going to write a special port number, which is its assigned port number, and let's say the port number is 12,001, okay? And so it's going to have to keep track of the source, the original port number. Okay, and the reason you need to keep the original port number is because we have to make sure that we're going to put it back in again, okay? And we can't just use the source port number from the source over here, because it could be the case that both of them happen to use the same source port number, okay? The source port for both of them could be the same. We have no control over that. So we have to make sure they're distinguished from each other. So it's got to be the NATS port number. So the original port number, well, let's say 1, 2, 3, 4, 5. And this original port number were also 1, 2, 3, 4, 5. That's perfectly okay. This will be 1, 2, 0, 0, 2. So this will be the outbound. Okay. So the table is a kind of bit mixed up, but let's work with it and you'll see how this works in just a minute. So let's say a packet starts from here, 192.168.0.0.2, and the source, this is going to be the source IP, and then the source port is equal to 1, 2, 3, 4, 5. Okay, here the source IP is this, and the source port, just to make life difficult, is also 1, 2, 3, 4, 5. Okay, so let's take a look at this packet over here. This packet goes to the NAT gateway. The NAT gateway says, okay, I just got a packet from source 192.168.0.2, and the source original port number is 1, 2, 3, 4, 5. What I'm going to do is I'm going to change the destination to my IP, which is 129.977.741, and I'm going to change the source port number, the outbound TCP port number, to 120.0.0.1. Okay, and I'm going to send it to the destination, which is this one over here. This destination sends a reply back, and the reply is going to contain this as the destination IP address, and the port number is going to be 120.0.0.1. When it sees 120.0.0.1 on the port as a port address, it says, oh yeah, sure, that was this entry over here. So what am I going to do? The NAT gateway is going to replace the destination with 192.168.0.2, replace the port number with 12345, and give it to this laptop over here, because that's the destination, 192.168.0.2, 12345, and this application over here gets a packet as if it didn't know something was done under the cover. When this laptop or the V device over here sends a packet 192.168.0.3, it comes over here. This one enters this entry into the table, not that one. It says, okay, I have a source port of, this entry over here is 192.168.0.3. The outbound port number shouldn't be here, 120.0.0.2. And then the destination is 128.32.16.8, and the original port number was 12345. That one is not needed. And it makes that entry over here, right? And when the reply comes back, it says, okay, when I get a message from 128.32.16.8 on port 120.0.0.2, I know I should change the destination to 192.168.0.3 and the destination port to 12345, which means it will actually come to this V over here, and everything is fine. So what you're seeing over here is that, in some sense, this outbound TCP port number is giving us additional bits of address, which we can reuse, because that allows us to distinguish between all the different sources. I'm going to move on to these topics of MAC addresses, ARP, and routing in a LAN. Okay, and let me start with MAC addresses. So let me just draw the stack again so far. So if you have application layer on top of the transport layer, that's on top of the network layer. And now we're going to sort of get a little bit into the next layer, which is called the link layer. We'll return to this in 2 lectures in more detail. And then below that is what's called the physical, which we won't talk about at all. But I just want to talk a little bit about the link layer for now, because it turns out that what the network layer does depend a little bit on the link layer does. So just to remind you, this is like TCP or UDP. This is like IP. Here, the most common link layer is Ethernet. There are many other link layers, but I won't talk about them very much. I'll talk mostly about Ethernet because it's like 99%, more than 99% of all links are Ethernet-like links. So the link layer is giving you the abstraction of a link, just one link, one point, another point. And we have two kinds of links out there. One is called the point-to-point link. This just goes from one end to the other. And if you recall, point-to-point link can be simplex or duplex or half duplex. We talked about it in the first lecture. Okay, so simplex means it goes this way or this way. That's simplex. And then duplex is bidirectional. Okay, and it's duplex. And then half duplex means it's simplex, but you can change directions, but you can't have both at the same time. So anyway, that's a point-to-point link. Another kind of link, and that's the kind of link we're going to think about from now on, is what's called the broadcast link. And what you can think of as a link that looks like this, where you have some intermediate hub, or we call this a hub, where any packet sent on anybody goes to everybody else. Okay, and this is a wired imitation of a wireless broadcast. So if you have radio broadcast, your transmitter, okay, it's on top of the hill near Kitchener, and everybody who has a radio can listen to it at the same time. That's a broadcast. When you want to do it with wires, you essentially have some kind of hub, and whenever any packet goes from here, or we call it a frame at the link level, the frame is received to everybody else. And the same is true for anybody else. If this guy puts out something, everybody else gets it. And that's the way hubs work when you have something at home. So when you have a hub at home, you put in your wires into it, and they all kind of talk to each other because we have essentially what's called a broadcast medium. Okay, broadcast medium. Now the other way to get a broadcast medium is to have some kind of access point, and then actually have wireless, and then everybody who has an antenna is going to be able to listen to the broadcast, and that's of course a broadcast as well. So Wi-Fi works like that. So anybody in Wi-Fi range gets the broadcast, and that's a kind of a natural broadcast, no wires. Okay. So any questions about broadcasts? Okay, bidirectional broadcast. Anybody can broadcast to anybody else. If we have broadcasts, then turns out doing routing becomes really simple. And the way it works is like this. Each destination endpoint has an address. Okay, and we call this address a medium access address, because this is the broadcast medium. It's the address you use to access the medium. And being networking people, we of course abbreviate it to MAC. That's a MAC address. It's a medium access address. And you might ask, why don't we use IP? What's wrong with IP? Why don't we use IP as a medium access address? And the answer is that you could, right? Theoretically, you could. There's no particular reason why you can't do it, because certainly the IP addresses are unique inside any subnet. And historically, these medium access protocols or medium access addresses were devised independently of IP, right? So the medium access addresses or MAC addresses are specific to particular technology like Ethernet. Apple had something called Apple, what is it called? Apple Works, not Apple Works. I forget the name right now. Apple Talk. So Apple Talk was its own medium access protocol. Xerox, of the photocopy company, used to have networking business, and they had something called XNS, Xerox Networking Services, and they had their own MAC addresses. IBM had their own MAC addresses, and so on. So the vision was that IP would work on all these different kinds of link layers. It would work on Ethernet. It would work on IBM. Okay, it would work on digital. Had something called DNA, digital network architecture, etc. And IP would unify all of them, and they all would use different MAC addresses. Of course, what's actually happened is all of these have gone away except Ethernet. So today you could say, yeah, why bother? But in the days that IP was invented, there were many different medium access addresses, but all of them had this property that they were broadcast. Okay, so two things. First, every endpoint over in here has a unique medium access address. And second, this address is not the IP address. And third, in order to get from here to there, you need to have the medium access address. And the way it works is that the source on its frame will have a destination MAC address, okay, and it broadcasts it to everybody. Each endpoint looks at that address and says, is it my address? If it is my address, great, I'll take it. If it's not my address, I'll just drop it, right? And that's it. That's the way it works. Okay. So that's how routing works. It's really pretty straightforward. Of course, the source needs to know the destination's MAC address somehow. So we come down to two questions. The first question is, how do interfaces, because that's really what a destination is, get a unique MAC address? And the second question is, how can a source learn the destination's MAC address? Okay, two questions for us to figure out, and once we figure it out, we pretty much know how to route within the LAN, how to get data inside a LAN, which is the topic that I want to talk about over here. Okay. All right, so let's see how that works. So I'm going to focus on broadcast links. I'll leave the broadcast up. And it doesn't matter whether it's wired or wireless. So, okay, are these questions clear? Okay, so let's start with the first one. How does the source get a unique MAC address? Now, we could do it the way IP does it, right? We could go to a registrar, Aaron or whatever, and say, give us a block of MAC addresses, and I want to assign the MAC addresses and so on and so forth. But that's not the way it's done. Again, historically, the way it's done is that to get a MAC address, it's actually extraordinarily simple. The MAC address consists of two parts. It's usually, for Ethernet MAC, to be more precise. And this is both for wired Ethernet and wireless. Wireless meaning Wi-Fi. They both have this two-part structure, which is 3 bytes, okay, 24 bits, is the manufacturer ID. And then the remaining 24 bits is the serial number. Okay, and that's it. So manufacturers go to the person in charge of the MAC addresses, which happens to be IEEE. The IEEE is the Institute of Electrical and Electronic Engineers, and goes to IEEE. You pay $1,000, and they give you a manufacturer ID. They don't really charge much for it. $1,000 is not very much, because you can have 2 to the power 24 manufacturers, which is about 1 million different manufacturers, and there aren't 1 million manufacturers of Ethernet interfaces right now. They're probably like 5. Okay, so yes, way more than you actually need, and so yeah, it's not a big deal. You can go to them. So you put this one over here. For example, this could be 0030E8, that's 24 bits, and then you can put 000001. So manufacture 0030E8. That's the first Ethernet card they manufacture. The second one will be 01, 02, all the way up. And they can make 2 to the power 24 devices, and then they ask for one more manufacturer ID and so on. And there's plenty to go around, because we have actually got a total of 48 bits. Okay, and that's more than enough, even though estimates are that about 2 million Wi-Fi devices are sold every single day. Okay, about 2 million a day is what people are selling. About 750 million Wi-Fi devices a year. Okay, let's still go around. Why 0030E8? It's my MAC address. I paid $1,000 for it, and it belongs to me. Okay. So these are unique. Okay, these are unique addresses, and that's how interfaces get unique MAC address. Okay, it's really simple, and they're guaranteed to be unique because manufacturers make them unique. They do not have geographical locality, right? They don't have that. So that's why we have to use broadcast. We can't make routing tables with them. Okay, because this MAC could be coming from Apple, this could be coming from Dell, this could be coming from Cisco, and this could be coming from whatever, D-Link, and they're all different IDs. So, we're going to have the table. Remember, we started out by saying we're going to have a table, lookup table, and that would be crazy. If you have 1 million MAC addresses, you're going to have a table of size 1 million because there's no way to aggregate them up. Okay, there's no way to aggregate them up. There's no geographical locality. So, in fact, the system I showed in the beginning, which showed the tables being very large, exists in practice, and that is, in fact, the way the Ethernet works. Okay. So, let's look at the second question. How can we source learn the destination's MAC address? And the way we do that is using what's called the ARP, which is the Address Resolution Protocol. So ARP is the Address Resolution Protocol. And to show how it works, let me give you an example. And the example I'm going to use is how you set up a laptop at home, right? So let's say you get a laptop at home and you are going to, you want to basically use it to connect to the internet, so you need an IP address, right? And let's say you have purchased a DHCP server, which is part of your NAT. So you typically have a NAT/DHCP and a firewall, okay, all in a single box. It'll probably be typically like a cable or a DSL. This combination is typically DSL plus cable modem. So you can buy it for about $40. You can buy a DSL cable modem with a NAT and DHCP, so it's all in one. Most of you probably seen. Has anybody not seen one of these devices? Okay, so you know what it looks like. So let's see how it gets set up, right? The first thing this device needs to do when it gets plugged in is for it to get an IP address, right? So the way it does is, it first does a MAC broadcast saying, I need an IP. Okay, and it's saying, it's a MAC broadcast is an address, a MAC address, okay, which is basically the last 3 bits are all ones. Last 3 bytes are all ones. So if it's all ones, that's the broadcast address. And that's kind of encoded. So if you put all ones, it doesn't matter what the manufacturer is. That means everybody is supposed to listen to it. All devices will accept it as being, it matches them. Okay. So the source knows it, so it sends a broadcast MAC, puts a broadcast MAC address saying, help me, my source MAC is whatever, because you have a source MAC, it's hard-coded. It's in the hardware, right? The manufacturer burnt it into the ROM. Okay, and so it's like this address, for example, and it broadcasts it, and so the DHCP server is going to get it because it matches, it's a broadcast. It looks as, okay, there is some source which has this source MAC, which needs IP address, I'm going to give it one. So it gives it a MAC IP address, says here you go, and this is your IP is something, okay? And now this source is the IP address. And it's going to say plus the router's IP is something plus the subnet mask. I'll come to subnet mask in just a minute. Okay. In about 5 minutes, I'll come to subnet mask. But it's going to give you your IP, the router's IP, and the subnet mask for your subnet. Okay. Now, let's ignore subnet mask for a moment. And so with this, the laptop has its own IP. That's great. And it knows the router's IP, but it doesn't know the router's MAC address. It just knows the router's IP address. How does it find out the router's IP address? Same thing. It sends a broadcast out saying, it's called the Address Resolution Protocol, ARP broadcast, which says, hey, I have this IP, which is a router's IP. Can you tell me what your MAC is? Okay. And the router, which need not be the same box, but usually is, comes back and says, my MAC is this. Okay? So that's it. So because you know that everybody can receive a MAC broadcast on the subnet, right? That's by definition of a subnet. Everybody can receive it. You broadcast it, everybody gets it. One of them is going to have the router's IP. Again, by definition, it's in your subnet, right? And so at this point, the router can recognize that it is the one which has that IP address. So it responds back and says, this is my MAC. Once it gets this, this laptop can just use the MAC address and doesn't have to broadcast anymore. It can just basically use that MAC address, and then nobody else has to receive it. When you do broadcast, every host on the network is forced to receive it. Okay, so if you have a local area network with 1,000 hosts and you send one broadcast packet, all 1,000 have to receive it and see whether it's something for them to do. But if you have a broadcast which has their destination MAC on it, only one destination MAC on it, everybody else, the hardware will drop it for them and never touches the software. So it's pretty efficient. So let me kind of run through this once more just to make sure you get it. The first thing you have to realize is that in Ethernet or in a broadcast medium, which Ethernet is, every destination, every interface has its own medium access address, or MAC address, which is burnt in by the manufacturer. And we get uniqueness by having the first 3 bytes being the manufacturer ID and the next 3 bytes being a serial number, so it's unique. The way we send data is that anything that's sent out actually is automatically broadcast, but only one destination which matches the destination address is going to do any processing on it. Everybody else just drops it. However, if the broadcast address, which is this one, all once is set, everybody must process it. That means the hardware is going to hand it up to the software IP, and the IP has to do some work on it. So in this case, what happens is that so we use this for 2 different protocols. One is for DHCP, one is ARP. So the way DHCP works is that you do the MAC broadcast and everybody receives it, including the DHCP server, which then processes it and says, okay, here's somebody who needs an IP, gives them the IP, gives them the router's IP, subnet mask. It also gives them like a lease time. If you remember, it says you can have this address for so long. There's a lease time. That's part of that as well. But it doesn't give you a MAC address. And that comes to here. Now this knows the router's IP, but doesn't know the router's MAC address. So it does another broadcast, which is ARP. And the ARP broadcast says, hey, I have your IP, I have this IP address. I want to know your MAC address. And then it replies back saying, okay, this is my MAC. Again, this is guaranteed to work. At this point, this laptop knows its own IP, and it knows the MAC address of the router. And so at this, from now on, whenever it wants to send something to the rest of the world, it will put the router's MAC address. Okay. And then it goes to the router, and then off it goes into the world. Okay. What happens is you want to talk to somebody who's not out in the world, who's local. Right? So you have 2 devices in the same subnet and they want to talk to each other. How does that work? So let's look at routing in the LAN and see how that works. So we have the following problem. We have let's say it's a laptop and there's another device, let's say another laptop, or let's be modern, we'll have an iPad even, wow, and a playbook. We are in Waterloo, we should have a playbook even. Okay, so everybody else can have an iPad, but we have playbooks. Okay, and they're all in the same, they're all connected to the same hub, like so. And that's your hub over here. And in addition, the hub is connected to some router, like so. And maybe that's also a NAT, but we don't care about the NAT for right now. That's something that just happens. Okay, so, okay. All right, so the question we have is this: how do these guys talk to each other? All right, and how do you decide whether to talk to this router or to this? Okay, I mean, what does it mean to talk to them in the first place? To make things a bit concrete, let's give them some IP addresses. So the 192.168.0.2, this is a .3, .4, .5, and usually the router would be the .1. That's just the convention, so we'll use that. And it's all on 192.168.0, so it's 192.168. 192.0.0/24. That's the subnet that it's in. Okay. So the first thing that when you get a laptop, let's focus on this .4 laptop, this one over here. You remember that when you configured it, it got three things. It got its own IP, which is 192.168.0.4. It got the subnet mask, and the subnet mask is really /24, but written out in a different way. And the way we write it is 255.255.255.0. And as you can see, this is really /24, but just written out a different way. It's just actual mask written out, right? And then it also knows the router's IP. And the router IP is 192.168.0.1. And all this stuff, all this information comes from DHCP. So all of them have this information here. Okay? Everybody clear on that? So I'm just repeating what I just said earlier. And so, okay, so now we have the following question. This .4 wants to talk to, let's say it wants to talk to two addresses. So one address is 128.32. Let's say 16.8, and the other address wants to talk to is 192.168.0.5. Okay, so those are the two addresses it wants to talk to, and it wants to know what to do, right? If you think about it, when it wants to talk to the first address 128.32.16.8, what it has to do is to send an IP packet, but the IP packet should be having a destination MAC address of the router's MAC address. Okay, let's call this. So this is .1. Let's say destination. The MAC address is our MAC. Okay, let's just call that R. That's a MAC address. So we want to create a frame where we always have this. So the IP address is going to be 128. Let me actually draw this bigger. So we have the data over here. And the IP address is 128.32.16.8. Now, from the perspective of the MAC, this whole thing is the MAC data. And the MAC header is going to be the router's MAC. MAC is going to be the MAC destination field is going to be the router's MAC address. Okay? You see how we're encapsulating, right? The IP header and data are put inside a bigger envelope, which is the MAC frame, which contains the MAC destination, of course, the MAC source, and a few other fields. We'll come to that later when we talk about the link layer. And this whole thing, from the perspective of the MAC, is just data. It doesn't really know what it means. Okay? And inside the IP data could be the TCP header stuck in, for example. Right? The TCP would be inside the IP, or the UDP would be inside the IP. Okay? That's what we want to do for the first thing. This is what we want to do over here. When we want this other one, we want to create a frame that looks like this. We want the destination IP address to be 192.168.0.5. You want some data. Of course, this is the IP destination. And in front of it, we want, let's call this the 5. Let's just call it the 5 MAC, just to distinguish. This has some MAC address, and we want 5 MAC over here as the destination, the MAC destination. Okay? That's what we want to do in the software. So how do we do it? Okay? So the way we do it is that first we need to recognize that this IP address is not in the subnet. And this IP address is in the subnet. Okay? If the IP address is in the subnet, we can discover the MAC address, 5 MAC. We can discover this MAC address using what? ARP, right? So we discover this using ARP. Okay? If it's not in the local subnet, then we discover this RMAC also using ARP. Okay, but we have to discover not the IP address. We can't broadcast 128.32 16.8 and say, give me the MAC address for that, because nobody knows that. We have to broadcast the router's IP address and say, give me the MAC address for that. Okay, so ARP cannot resolve this IP address, but it can resolve 192.168.0.1 over here. Okay, so how do we decide this? The way we do it is very simple. We take the destination IP address, and mask it. That's the bitwise and the subnet mask. Okay, and we say if destination IP and subnet mask is equal to my IP and subnet mask, okay, if this is true, then local, okay, which means destination MAC equals our MAC, else local is equal to MAC equals for destination MAC, get des MAC from ARP. Okay, else remote, which means destination MAC equals our MAC, the router's MAC. Okay, so what are we doing over here? We take, for example, in this case, our subnet mask is 255.255.255.0, and we take these bits over here, 192.168.0. Okay, and this one, it takes its own IP, 192.168.0.4, and masks it and finds that this is 192.168.0. These match. If these two match, then the destination IP address is in the same subnet. Okay? If it's in the same subnet, it must be the case that we can resolve it using using ARP. So it's local. We get the destination MAC using ARP. What do? We broadcast on ARP and say, hey, I have this IP address 192.168.0.5. Who does it belong to? And the 5 responds back saying, my MAC is 5 MAC. At this point, you can establish communication. For this could be, for example, a printer. And that's how printers work. Wireless printers, that's how they work. Okay? So that's routing inside a LAN. That's how that works. Okay? Any questions about this? Okay, so just to repeat, what's going on is that we just need to know whether it's local or not. Okay, it's local or not. If it's local, we use ARP. If it's remote, then we have to give it to the router. So we find out the router's MAC address, and at that point, we're done. Okay, and that's basically how routing in a LAN works over here. Good. So now I can move on to the next topic. I didn't think I'd get to it today, so I'm going to talk about that instead. So I'll just add it here, because I got this. This is the graph abstraction, and that will set up nicely for the next lecture. So let me talk about the graph abstraction here. Okay, so I want to show you a way to represent a network which is a model for it. It's not the reality, it's not actual wires and actual interfaces and actual anything, but it allows us to manipulate the network and understand it in a really nice way, and that's modeling it as a graph. So what do I mean by that? What I mean is something like this. Let's start with some actual devices. Let's say I have a couple of laptops, and they have that the iPad and my playbook, the same system I had over here before, okay, connected to a hub, and this is connected to some router, okay, and this is all in one subnet, and the typical way we represent it in the same subnet is to draw a cloud around it. That's your subnet cloud. Okay, and this router, if it's at your home, would go and would be talking to a router that belongs to, let's say, Rogers router. They have a router in their central office. That's a router over here. And that's talking to another router at somebody else's home over here. And it's the same kind of cloud like that. Okay? And maybe the others as well. And I'll just draw these puffs. And I'll draw another one and just draw a circle. Okay? And now from here, you can see I've gone to a node and an edge. Okay? And I can do the same thing again. So I have this router over here, and that's connected to some, maybe they have a connection to two other routers, like so. Okay? And maybe that's connected to some other set of homes. This is connected to some set of homes. Okay? Now, maybe something is connected to University of Waterloo. How would that look? Typically, University of Waterloo will have two different connections from two different routers to two different internal routers, just because we want redundancy. And then inside the University of Waterloo, what we do is we typically have connection one. Each of these is connected to one of departmental routers. We have a bunch of these, like so. This is the way it's actually set up. Bi-connected. Everybody has got links from both of them, so it's always an alternate path to get to the external router. These two things are in the basement of Math MC. These are connected to a bunch of switches. And then these switches are connected to hubs, and the hubs are connected to endpoints. So it looks like a mesh over here and looks like a tree out there. But from our perspective, we can draw all of this as one big cloud, and we can call it 129.97.0.0/16. And if it's connected to some other university, okay, let's say it's connected to McMaster, that would be something like that. And if it's connected to yet another university, maybe from here, that could be yet another, I'll just draw a circle. What I'm getting to here is that although there's quite a bit of detail over here in terms of how everything looks and so on and so forth, and how this looks over here, to some extent we can represent it just using circles and lines, okay? And we can draw it as a graph. And so if I were to just consider this part over here, I could draw this section over here as this graph. I have a router, and then connected to it, I have a bunch of, we can ignore the MAC, okay? They have these four, this is this network over here. So this hub kind of goes away because at the IP level, hub doesn't exist. The router, as far as we're concerned, is one hop away from all of these guys. We can represent this chunk over here, okay, similarly as just being something like that, okay? And we can represent this stuff over here, in fact, I've more or less drawn it the way it should be, just, circles, instead of rectangles, I draw circles. But it all becomes just a graph, okay? And that's what we call the graph abstraction, okay? So the graph abstraction is a way for us to represent the different paths in a network using just nodes and edges, okay? And so let me draw a graph like that. Now removing all this. So I would say that here is a network now. And when I draw this, it looks pretty abstract, but each circle is really, when you open it up, is a network or a subnet, okay? Each of this is a network or a subnet. Okay. So far, so good. Now we can actually talk about something interesting about this representation, which is I have a node A here, which is inside here, and we'll call this node B, and I want to send a packet from A to B. Perfectly reasonable thing to do. How should I do it, right? It turns out there are many different ways of doing it. I could go like this, okay, that's kind of long and windy, or I could go like that, okay, or I could go like that. and so on, right? It's like going to if you have two destinations connected by a network of roads, there are very many different ways of going from one to the other. Which one should I pick? Okay. It turns out that solving this problem is quite hard, okay, because these links and these networks have some complexity, and each link is characterized by things like its cost, its capacity, how many bits can it send per second, how much delay it introduces, and how much loss it introduces. Okay, it may be very lossy links, for example. So if this is very lossy, I might actually prefer to go around this way. Or if it's very congested and the losses are happening due to congestion, I may want to avoid it even though it takes longer. Okay, so what we do with this graph abstraction is to take this network like so, and we associate with each edge a weight, okay? And the weight represents the goodness of the link in some way. Okay? So if typically the lower the weight, it's better. Okay, so for example, if you have a high capacity link, I can say it has a weight of 1. This could be a weight of 10 because it's lossy. That's 1, that's 2, 5, 6, something like that. And then my job becomes finding a path from, let's say, A to B such that the path has the shortest sum of link weights. Okay? And that's what we want to do. So here, for example, if I take this path, it's 1 plus 3, 4, 5, and that's 11. It's 4, 6, that's 11 again. And if I go this way, it's 16. So maybe the path I should take is something like this, okay? That's the shortest path probably in this thing. So how do I find shortest paths? So in the next lecture, which will be, I guess, almost a week and a half from now, I'll start with this graph abstraction and show you how we can use a couple of different approaches to compute shortest paths. Okay, and then we'll talk about how these are actually used in internet routing protocols. Okay.